Okay, next section, intermolecular forces. The physical properties of molecular substances result from different types of forces between their molecules, and there's three main types of forces that we have to talk about. These London forces, dipole-dipole forces, and hydrogen bonding. Now we have to be a little bit careful. Previous courses will have talked about the term van der Waals, but that's actually a term that covered a couple of these. So we're going to break it down and be talking about London forces, dipole-dipole forces, and hydrogen bonding. And the relative strength of these London forces are much weaker than dipole-dipole forces, which are less than hydrogen bonds. And it's important to note at this stage that they're nowhere near the same strength as a covalent bond. Right, so if you are boiling a kettle of water, right, you boil the water, your kitchen doesn't blow up, you don't release hydrogen and oxygen because you're not breaking covalent bonds. You're overcoming the intermolecular forces when you go from a liquid to a gas. Right, so these London dispersion forces, they are temporary forces. They arise because our electrons are constantly moving around, and at any one time they might be at one end of a molecule, or atom, which will mean at the other end we've got a slightly positive charge, and that can induce a dipole in an adjacent atom or molecule. And they're in everything, right? And they become maybe more significant as we get bigger, as we get more electrons. So if we think of fluorine, it's a gas, chlorine, gas, bromine at room temperature is a liquid, and iodine's a solid. It's because we're getting more of these London forces. So there's more electrons in the iodine, there's more chance of these movements. We're getting slight positives, slight negatives, which are inducing charges in the next one, and we're getting slight attractions. And as a result, at room temperature, iodine's a solid. Likewise, if we have a longer chain, then we find that the melting point, boiling point also increases because we've got more of these forces of attraction, more of these London forces along the length of the molecule. An example there would be methane, which is a gas. Pentane at room temperature is a liquid. If you think of a plastic bag, that's essentially just long chains of polymer molecules. And so when we have enough of them, we find that those forces of attraction are significant enough that it's a good solid at room temperature. Dipole-dipole forces. Now we talked in the last section about polar bonds, and if we have a polar bond like that, we know that we've got one end that's going to be slightly negative, one end that's going to be slightly positive. And so if we draw on another molecule like that, that end's slightly negative, that end's slightly positive, what we find is that there is a weak force of attraction between them, and we describe this as a dipole. This is also a dipole, that's a force, so it's a dipole-dipole force of attraction. Sometimes, as I said, whilst we've maybe got a polar bond, the problem is we've not got a polar molecule, and we're not going to see these dipole-dipole forces of attraction. So this has probably got good London forces because it's quite big, but it's not going to show the dipole-dipole forces that we've got here. Likewise, carbon dioxide is also too symmetrical. If we draw out its Lewis structure, looks like that. Oxygen's more electronegative, so yes, we've got a polar bond, but we've also got a very symmetrical molecule, and so that isn't going to be able to do this kind of thing that we saw up here. So that's a gas at room temperature. Something like this, bromoethane, is going to be polar. We've definitely got a polar bond here, and we've got a polar molecule, so we can have interactions with another molecule as well. And these polar bonds here, when we talk about the organic chemistry section, it's going to be important how these haloalkanes, as they're called, react. This polar bond determines a lot about their organic chemistry. Hydrogen iodide, again, yeah, situation like this. Phosphorus pentachloride, or chlorine, yeah, probably is more electronegative than phosphorus. But if we draw out its structure, which looks like this, whoops, then it's too symmetrical. Right? It's too symmetrical, so we've not got one negative end, one positive end. Whereas, if we take this one, which has got an H instead of one of the Cl's, then yes, suddenly now we do have a more negative end to the molecule, and as a result we can start to see some of these dipole-dipole forces. Now the hydrogen bonding is kind of an extension of that, or extreme case of it. If we have a hydrogen attached to an N, an O, or an F, we can talk about hydrogen bonding. These are our most electronegative elements in a periodic table, particularly this one. And it means that if we take some water molecules, OH, we can draw similar diagrams to what we had a moment ago. Here's another water. Then there's going to be a force of attraction there, and we would refer to that as a hydrogen bond. And it's going to be stronger than just that dipole-dipole force. And it gives us some unusual trends. So it means that the boiling point of water is 100, which is not what we'd expect without hydrogen bonding. So thanks to hydrogen bonding, then it means life on Earth is possible because water exists as a liquid at the conditions that we live at. Likewise here, this is going to show hydrogen bonding, these ones don't, so we'd expect that one to be a bit higher, and then the rest start to creep up, because as we get bigger and bigger and bigger, we get more of these London forces, and as a result, the boiling point, melting point climbs up again. But we've got this anomaly here because of the hydrogen bonding. So physical properties, well, you've maybe come across the saying that like dissolves like in the past. And if you think of what the intermolecular forces are in your solvent, something like water, we've said that that's going to show hydrogen bonding. That's going to be good for dissolving things like ethanol, which also shows hydrogen bonding. What it won't dissolve would be something like hexane, which only shows London forces. So these two won't mix. So oil and water won't mix because this will keep doing London forces with itself, this will keep doing hydrogen bonding with itself, and they're not going to be interacting and mixing together. So that's where that saying like dissolves like comes from. It can have an impact on volatility. So the stronger the intermolecular forces, then the less easy it is for some of the particles to escape as a vapor. So something like ethane, that's already going to be a gas at room temperature, but ether very readily forms a vapor, because its intermolecular forces consist of dipole-dipole. This end of the molecule slightly negative, this end slightly positive. This one, ethanol, as I said down here, there's an H attached to an O. It's going to be able to show hydrogen bonding with another ethanol molecule. And as a result, that's stronger, so it's less easy to escape, so it's less ready to form a vapor. Now, electrical conductivity, really the only covalent substance that we'd maybe think about that could conduct that we've covered so far is graphite, and we said that that had spare electrons that were able to move around, but generally speaking most of our electrons are tied up in covalent bonds, so it's rare that covalent compounds conduct electricity. Of course, metals, good conductors, and we'll talk about metallic structure in a moment, but that's because they have delocalized electrons. And for ionic substances, as discussed in that section, when the lattice breaks down, then you find that you get the free moving charged particles in the form of the ions. So whether you dissolve it, whether you melt it, you get the ions that can move around and conduct a charge. Right, that's what we've covered, talked about those. Thank you very much.